Welcome to Lecture 9 Advanced Calculus. Today we are treating Extreme Value Theorem Section 3.2 of the text Advanced Calculus by Patrick M. Fitzpatrick. This is Dr. Gilbert Eyabi. Subsection 3.2.1 Definition. Let us consider the function f from the domain D to the set of real numbers R, and define the image set f of D to be the set of all f of x, where x is from D. Then f of D is the image of our function f from the domain D to the set of real numbers. A couple of things about f of D. We would say that the function f from the domain D to the set of real numbers attains a maximum value provided that the image set f of D has a maximum value. In other words, I can find an x0 in D such that f of x is less than or equal to f of x0 for every x in D. Observe that this is simply the definition of f of D being bounded above. But in this case, since f of x0 is a function value, that means f of x0 is an element of f of D. F of x0 is the supremum of the set f of D. We did prove before that if a set is bounded above and the supremum of the set is in the set, then that set has a maximum. As a matter of fact, the maximum is the supremum. So this is what we have here. F of x is less than or equal to f of x0. Our f of x0 is a function value, so that is the supremum. So f of x0 is the maximum of the image f of D, and we would say that the function f attains a maximum value at the point x0. x0 is of interest to us. Since f attains a maximum at x0, we will call the point x0 a maximizer of the function from D to R. Similarly, we can define a minimizer of a function f from the domain D to the set of real numbers. So that would be the point at which f of D attains a minimum value. F of whatever it is, x1, is the smallest value in the image set f of D. I would leave that for you to give a complete definition. Thus, we can say that a function f from the domain D to the set of real numbers has a maximum precisely when the image f of D is bounded above and the supremum of the image is a function value. That means the supremum of f of D is an element of f of D. In general, no assertion can be made concerning the existence of a minimum or maximum value for a function f from a domain D to the set of real numbers. But we would be able to make a definite assertion if D is a closed bounded interval, and that is the key theorem of this section. Now, as a quick review, what we are saying is that the function f from D to R attains a maximum if there is an x0 in D such that f of x is less than or equal to f of x0 for every x in D. And once more, f of x0 is a function value and it actually equals the sup. F of x0 is the maximum value and x0 is known as the maximizer of the function f from D to R. Similarly, we say that the function f from the domain D to the set of real numbers R attains a minimum value if there exists a t0 in D such that f of t0 is less than or equal to f of x for every x in D. When that happens, we say f of t0 is a minimum value. Recall, f of t0 is also a function value, and therefore it equals the infimum of the image set. F of t0 is known as the minimum value, and t0 from D is known as the minimizer of our function f from the domain D to the set of real numbers. Now, let us look at a few examples, and I want you to think a little with me as we move on with these examples. If a function is continuous on a domain D, is it necessary that that function would have minimum and maximum values on the domain D? What if D was just an open interval? What about a closed bounded interval? What about an interval that is bounded but not closed, or closed but not bounded? So I need you to look for examples of functions that are continuous on such intervals and see if you can argue that f would always have a maximum and or a minimum on those intervals. Can you always find some x0 such that f of x0 is a maximum value, or some t0 such that f of t0 is the minimum value? We would prove that we can only confirm the existence of maximum and minimum function values if D is a closed bounded interval. Now let us start with this example. Define the function f from the open interval 0, 1 to r by f of x equals 2x. Then f is a continuous function on this interval. Polynomial functions are continuous on R, so in particular, f of x would be continuous on the interval 0, 1. Would it attain a maximum and or a minimum value on 0, 1? Well, let's look at it. Then f does not have a maximum value, since no matter what x0 you pick in the open interval 0, 1, all the points in x0, 1 have functional values greater than f of x0. Remember, there are infinitely many points between 0 and 1. So if you pick a point x0, between x0 and 1, there are infinitely many values, and all the values that are in the interval x0, 1 will be greater than f of x0. So f does not have a maximum value on this interval. So this is an example where our set D is bounded, and as a matter of fact, the image f of D is also bounded. The supremum of f of D is 2, but the function has no maximum. Why? Because the supremum is not an element of f of D. And that happens because 1 is not an element of the open interval 0, 1. So if we look at the graph, y equals 2x is this graph right here, and it is opened at 0 and open at 1. So there is no maximum value, there is no minimum value on 0, 1. It does not attain to a maximum value or a minimum value on the open interval 0, 1. An example of a function continuous on a bounded interval. The image set is bounded, but it does not attain to a maximum or a minimum value. Example 2. Define the function f from the open interval 0, 1 to r by f of x equals 1 over x for every x in the interval 0, 1. Observe that f is continuous on this interval because the denominator does not vanish. But if I pick my n to be a natural number, then f of 1 over n, observe that 1 over n is going to be an element in the domain, so that is defined. F of 1 over n equals n, which is unbounded. It is not even bounded above. Thus, the function certainly cannot attain a maximum value because it is an unbounded function. So this is an example of a function that is continuous on a bounded interval, and the image set is not bounded and therefore does not have a maximum. So in the first case, f was continuous on a bounded interval, the image set was bounded, but it did not contain a maximum nor a minimum value. In the second case, f is continuous on a bounded interval, the image set is unbounded, and therefore it does not attain a maximum value. So When can we be certain that if f is continuous, then it attains a maximum and or a minimum value? This is the picture for the second example, that is f of x on 0, 1. It does not attain a maximum value because it is unbounded as we approach 0. As we have stated above, for both examples, f is continuous, but the domains D were not closed. They were bounded, but not closed. So we would show that if f is continuous on a closed bounded interval, then the image set would have both maximum and minimum values, and that is what we call extreme value theorem. Before we get there, let us look at a lemma. The image of a continuous function on a closed bounded interval f from D to R is bounded above. That is important. If f is continuous on D and D is closed and bounded, then f of D is bounded above. We just saw an example where f was continuous on an interval, but the image set was unbounded, and that was because D was not closed and bounded. It was bounded but not closed. So what we are saying is there exists a real number m such that f of x is less than or equal to m for every x in the closed bounded interval a, b. Let's go ahead and prove this lemma because we would need it in our proof of the extreme value theorem. Proof. We argue by contradiction. So we assume there is no such m such that f of x is less than or equal to m for every x in AB. So let n be a natural number. What we are saying by contradiction is that it is not true that f of x is less than or equal to n for every x in the closed bounded interval AB. If that happens, then we are saying that there exists an x value in our closed bounded interval AB such that f of x is strictly greater than n. So why don't we look at that particular point, the point x, such that f of x is greater than n? Let us call that point xn. If we do that, then this defines a sequence xn in the closed bounded interval AB with the property that f of xn is strictly greater than n for every natural number n. Now we go back to the sequential compactness theorem. Every sequence on the closed bounded interval has a subsequence that converges to a point in that interval. So, by the sequential compactness theorem, we can select a subsequence xnk of our sequence xn such that xnk converges to x0, which is a point in the closed bounded interval AB. But f is continuous on the closed bounded interval AB. That means f is continuous at the point x0. But what does that mean by our definition of continuity? Since xnk converges to x0, f continuous on x0 means that f of xnk must converge to f of x0. But wait a minute. We do know that every convergent sequence is bounded. It has a beautiful proof. If you have forgotten the proof, you should go back and look at it in section 2.1. Every convergent sequence is bounded. So we have f of x and k converging to f of x0. What does that say about the sequence f of x and k? That means the sequence f of x and k is bounded. But wait a minute. This contradicts the property that f of x and k is greater than nk, which is greater than or equal to k for every k in n. And this contradiction arises from our assumption that there is no m such that f of x is less than or equal to m for every x in the closed bounded interval AB. Therefore, we can conclude that if f is continuous on the closed bounded interval AB, then f of the closed bounded interval AB, which is the image of the closed bounded interval AB, is bounded, and that completes the proof. Now that we have the lemma out of the way, we can go straight into the core of section 3.2, the extreme value theorem. Subsection 3.2.3, the extreme value theorem. Very simple worded theorem. A continuous function on a closed bounded interval AB attains both a minimum and a maximum value. So if f is continuous on the closed bounded interval AB, we can say that there exists an x0 such that f of x0 is the maximum value and x0 is the maximizer, and there exists a t0 such that f of t0 is a minimum value and t0 is a minimizer. Very beautiful worded theorem. Let us look at the proof. Proof. Define S to be the image set f of the closed bounded interval AB. Then f is a non-empty set of real numbers, and by lemma 3.2.2, the one we just proved, f is bounded above. Now, but f bounded above, by the completeness axiom, it means S has a supremum. Let us call the supremum C. So let C be the supremum of S. What we want to do is to find a point x0 in AB such that C equals f of x0. This point will be the maximum value in S, and remember S is the image set. If that happens, then we would simply say that f of x0 is the maximum value in f of the closed bounded interval AB, and that would mean that f of x0 is the maximum value that f would attain on the closed bounded interval AB. So that is our goal. We have to show that there exists an x0 such that f of x0 is the supremum of S, which is C. Now let n be a natural number. Then C minus 1 over n is smaller than C, and therefore it is not an upper bound for the set S because C is the supremum of S. And if that happens, that means there exists an x in the closed bounded interval AB such that f of x is strictly greater than C minus 1 over n. We've seen this argument over and over again. So select such a point and call it xn. For this choice, and from the fact that C is an upper bound for S, that means C minus 1 over n is strictly less than f of xn, but f of xn is less than or equal to C for every n in n because C is the supremum of our set. So by the sandwich theorem, or the squeezing theorem, or the pinching theorem, as some people would say, since 1 over n converges to 0, we can see that the term to the left would converge to C. C converges to C, therefore we can conclude that as n approaches infinity, f of xn would converge to C. Hence, the sequence f of xn converges to C. Since xn is a sequence in the closed bounded interval AB, by the sequential compactness theorem, we saw this again in lemma 3.2.2. There exists a subsequence of xn known as xnk such that xnk converges to x0 and x0 has to be in the closed bounded interval AB. Once more, f is continuous on AB, which means f is continuous on x0 in AB. xnk converges to xn would imply that f of xnk converges to f of x0. We saw this argument again in lemma 3.2.2. But what we want you to observe here is that f of xnk is a subsequence of the sequence f of xn, and this subsequence converges to C, so our C equals f of x0. That means x0 is a maximizer of the function f from the closed bounded interval AB to the set of real numbers R. To complete the proof, we observe that the function negative f from the closed bounded interval AB to R is also continuous. Consequently, using what we have just proven, we can select a point in the closed bounded interval AB at which the function negative f from the closed bounded interval to R attains a maximum value, and at that point, the function f from AB to R attains a minimum value. Therefore, we can conclude that if a function is continuous on a closed bounded interval AB, then it attains both a maximum and a minimum. That brings us to the end of section 3.2, extreme value theorem, and I look forward to seeing you in section 3.3, intermediate value theorem. Thank you and God bless you.